Hello friends, welcome to today's machine learning class, and in this class we will see some more detail about the backpropagation algorithm in artificial neural network. That is, how the gradient descent and delta rules are utilized by this backpropagation algorithm. After that we will see the derivation of backpropagation algorithm for a single hidden layered neural network. The first one is gradient descent and the delta rule. Okay, if the training samples are not linearly separable, for example, this is our hypothesis space. Okay, this is weight and this is the error rate. This is the error rate or loss. Okay, so the training samples will be classified here and circle. These are triangles, another set of samples, and these are all squares, another set of samples. Okay, here the samples are not linearly classified. Okay, by using a single line we cannot classify those data. In this situation we have to use the delta rule that converges towards the best fit approximation to the target concept. Right here the delta rule uses this gradient descent to search the hypothesis space for possible weight vectors to find the weights that best fit the training samples. So for every iteration the weight value will be adjusted with respect to the output, that is the output of training sample, that we will see in the forthcoming slides, right. The basis of backpropagation algorithm is the gradient descent, which can learn the network with many interconnected units. Okay, a network is having more number of nodes which will be interconnected to each other. To learn all those things, we have to use the gradient descent, and it searches through the entire hypothesis space. Okay, so the entire thing is called as the hypothesis space. Hypothesis space, which containing different types of continuously parameterized hypotheses. And the purpose of delta training rule is training an unthreshold perceptron, that is a linear unit for the output O is O of x vector, which is equal to W vector multiplied by x vector. Here the x vector is nothing but the input and W vector is nothing but the weight which is assigned to this network. Okay, so the multiplication of these two will form the output, and a linear unit corresponds to the first stage of perceptron without the threshold. Next we need to compute the training error of this hypothesis of weight vector, okay, which is related to the given training samples. This is the formula for that, that is error of weight vector equal to half of the summation of TD minus OD whole square. TD is nothing but the target output and OD is the computed output. Okay, target output minus computed output whole square. Here D is a set of training samples. Okay, the training samples which we have given to the network, and TD is the target output of training sample D, this particular D, and OD is the output of linear unit of the training sample D. Okay, this will be given in the table, and this error of weight vector is half the squared difference between the target output TD and the linear output OD, and summed overall training example, that is using the summation symbol. Okay, so this is important here. So after every iteration we have to compute the error, and based on the error we need to adjust the weight, and the entire process will be repeated once again. The next one is visualizing hypothesis space. So this diagram explains the hypothesis space of the given example. Here we are having two weight vectors W0 and W1. Two plans are there, and the y-axis indicates the error or loss. Okay, error of the corresponding weight vector hypothesis, right? And here one arrow is there that indicates the negated gradient at the direction W0, W1. See, the arrow moves downwards, W0 and W1, which producing the global minimum along the error surface. Okay, global minimum, that will be somewhat here. This place is global minimum. So the error indicates the global minimum point of this entire hypothesis space. Next, the error surface E must always be parabolic with the single global minimum. Okay, for example, this is W0 and this is W1, and y-axis indicates error with respect to the W weight, otherwise called as loss. Okay, this is the hypothesis space. If we see this hypothesis space from this W0 plan, we will get this parabola. See, we will get the parabola with respect to this global minimum. This is the red color point is global minimum. Or otherwise, if we see this hypothesis space from this W1, again we will see the same parabola. See, this is the parabola. Here the gradient descent search determines the weight vector that minimize this E, minimize the error by repeatedly modifying in small steps. For example, suppose if we are here, the point is the sample is predicted in this place and global minimum is here. See, this is weight and this is the loss rate. Loss rate is very high when compared to the global minimum. So for each step it will reduce the weight and finally it will reach this global minimum. Okay. See, at each step the weight vector is altered in the direction. Which direction? Towards the global minimum, that produces the steepest descent along the error surface depicted. This is important. Okay, this process continues until it reaches the minimum, that is global minimum error. Okay, let us take this neural network as our example. Here in the input layer we are having three nodes, x1, x2, x3 are given to this input nodes, f1, f2, f3. Okay, and the output of f1 will be connected to the all nodes in the hidden layer, isn't it? In the hidden layer we are having four nodes, hidden 1, hidden 2, hidden 3, hidden 4, and the output we are having one node, that is output 1. Okay, so the input function 1 will be connected to all the hidden layer, and here the output is 1 1, the output of hidden layer 1, this particular thing, which is equal to x11 dot w11, because the weight is multiplied by the input value, and this is O12, which is equal to x12 dot w12, and this is O13, which is equal to x13 dot w13, and this is O14, which is equal to x14 into w14. Okay, like the same, this is O21, O22, O23, O24, and this is O31, O32, O33, O34, right? Okay, the corresponding values will be assigned to all the outputs, right? See, when come to here, this particular node, what will be the output here? O41, isn't it? So output 3 and this is output 4, O41, which is equal to x11 dot w11 plus x21 dot w21 plus x31 dot w31. Okay, see, all the first output will be connected to the hidden layer first node, and when come to here, this is output 5 1, which is equal to x 12 dot w12 plus x 22 dot w22 plus x 32 dot w32, and when come to here O61, which is equal to x 13 dot w13 plus x 23 dot w23 plus x 33 dot w33, and when come to here O71, which is equal to x 14 dot w14 plus x 24 dot w24 plus x 34 dot w34. Okay, this which is the value of O71, output of this particular node. Okay, and when come to here, all these nodes values will be summed here, right? Okay, suppose if the point lies in this place and this is positive slope, this is called as positive slope when with respect to the weight value and the error of weight value, that is loss. Loss is in the y axis. Okay, this is x axis is weight. Okay, the point sample point will lies in this place, then the slope, that is the gradient slope, is called as positive slope, because here the weight value is increased and the loss value will also be positive when compared to the global minimum. This is the global minimum, isn't it? Error of minimum weight E. This is the global minimum one. Okay, for each step what we have to do? We have to reduce the weight value as well as the loss value. So if we reduce the weight, then the loss will also be reduced. So for each iteration we have to reduce the weight until we reach the global minimum. Okay, so this is called as positive slope because the weight is lies on the positive side. Suppose if the example value lies in this hypothesis place, that is the initial weight is here, then the slope is called as, this particular gradient slope is called as negative slope. Negative slope. Okay, because the weight is in the negative side, we need to increase the weight. We need to increase the weight. So for each step we have to increase the weight, hence the loss rate will be decreased. See, for every step we have to increase the weight gradually. When it comes to nearby this global minimum, then the step size will be increased. Gradually we are going to increase this one. Okay. And now let us see the derivation of gradient descent rule. Here we need to compute the error E with respect to all the components of weight vector. Okay, for every input we are having corresponding weight vector. For all the weight vector we have to compute the error E, which is called as gradient of E with respect to W. So the symbol is this one, delta E of W, which is equal to dE by dW0 comma dE by dW1 comma etc. up to dE by dWn. Here delta E of W, that is the gradient of E with respect to W, its components are partial derivatives of E with respect to each of Wi. The training rule of gradient descent is W vector, which is equal to W vector plus delta W vector. Here we need to update the weight value W new, which is equal to W old plus delta W. Okay, delta W is the new computed weight. New computed weight. So with the help of the computed weight only, we need to update the new weight dW, this one. Okay, where delta W is minus n delta E of W. Here this n is the learning rate. The n is a learning rate which is a positive constant, and it determines the step size in the gradient descent search. So how many steps there to reach the global minimum. So global minimum is there, so it will take more steps to reach the global minimum. So this determined by the learning rate, that is the n. And next one, the negative sign is represent because we want to move the weight vector in the direction that decreases E. Okay, so the E size, that is the error, should be decreased. So we have to use the negative sign here, right? And the training rule can also be written in the component form Wi, which is equal to Wi plus delta Wi. So the computed delta Wi will be added to the Wi. This is the old weight, and this is the new weight. Okay, so the delta Wi, which is equal to minus n into dE by dWi. See here, differentiation of E divided by differentiation of Wi, which is the gradient obtained by the differentiating E means error. Okay, in the previous slide itself, we have seen error of W vector, which is equal to dE by dWi, differentiation of E divided by differentiation of Wi, which is equal to half the squared difference between the target output TD and the linear output OD summed over all the training samples, which we have seen in the last slide itself. See, this is differentiation of E divided by differentiation of Wi, which is equal to differentiation of 1 by 2 summation of D belongs to capital D TD. TD is nothing but the target output. OD is nothing but the original output, and the difference will be squared here. Okay, now we just put this half outside this summation, outside the differentiation, then we will get 1 by 2 summation of D belongs to D differentiation of TD minus OD whole square divided by differentiation of Wi. Okay, now we have to differentiate these things, we will get this one. Okay, 2 into TD minus OD into differentiation of TD minus OD divided by Wi. Okay, because square is here, accordingly we have differentiating these things. Then we just remove this 2 and this 2, and we know what is OD here. This OD is nothing but weight into input of the previous one, isn't it? Its input will be the output, corresponding output. Okay, we need to substitute this value with the place of OD. Okay, then we will get this one. So here the differentiation of TD is 0 and the differentiation of W with respect to XD, differentiation of W is 1. Okay, so the value is minus 1. This value will be minus 1. So minus XID will be come here. Okay, so this is the formula, right, where XID denotes the single input component Xi for the training sample D. So that we have substitute this in this place. Now we have to substitute this equation into this particular equation, because we know delta Wi, which is equal to dE by dWi. So we can easily substitute these two equations. Okay. Now we get delta Wi, which is equal to n summation of d belongs to capital D Td minus Od into xdi. Okay. Here n is the learning rate and Td is the target output and Od is the original output, and xdi is the corresponding input value for this particular sample D. Okay. Now the gradient descent algorithm for training units is as follows, that is 3 steps are there. The first one, pick an initial random weight vector. Initially we have to select the weight vector, that is training samples weight vector, and apply the linear unit to all the training samples, and then we have to compute the delta Wi for each weight, right, and update the weight Wi by adding the delta Wi with respect, then repeat the same process again and again until Td, which is equal to Od. And this is the algorithm for gradient descent. It accepts two inputs, training samples comma n. Here training sample is a pair of input and target value. X is the input vector and t is the target output. Okay, and the n is nothing but the learning rate. It is normally a very small value. Here we have taken 0.05 as our learning rate value. So the step 1 is initialize Wi to uh, a small random value. Okay, we have to assign very small weight to all the inputs. So for all xi we need to assign Wi. Initially we have taken a small value for all Wi. Okay, and step 2 is until the termination condition is met. Until the termination condition is met. When we meet the termination condition, if t equal to O, okay, t is target output, O is computed output, right. So initialize delta Wi is 0. Initially we have to assign 0 to delta Wi for each training example xt comma x vector comma t. Do see input instance x vector to the unit and compute the output. See, for all the nodes in the network we have to give input, that is xi, and the node will produce the output oi. Oi means the computed output. Y is nothing but the computed output. Okay, and for each linear unit weight Wi we have to compute delta Wi, that is the error rate, okay, which is equal to delta Wi plus learning rate into the target output minus computed output and multiplied by the input value. This is learning rate, this is target output, this is computed output, this is the input value, x is the input value. So this will be done for all the samples. Okay, so after that we have to adjust the weight. We have to adjust the weight. When do we adjust the weight? If there is a difference between these two things. Okay, t minus O is 0. If t and O are not equal, then we have to adjust the weight of the entire network. Okay, so this is weight nu and this is weight old plus the error rate, adjusted weight. Okay, this thing, and this thing will be done for all the until we meet the termination condition, these things will be repeated. Okay, so this is called as gradient descent algorithm. So up to this we have seen the backpropagation algorithm in artificial neural network, and also we have seen how the gradient descent algorithm and delta rule are very important for solving the backpropagation algorithm. Okay, in the next class we will see the backpropagation algorithm for multi-layered neural network. So for more information, please go through your textbook. Thank you.